When you stop and think about it, what actually makes a river flow? Or, for that matter, what keeps the air in your tires? We're about to dive into the world of fluid mechanics, and I think you're going to be surprised how much of this stuff is all around us every single day.
All right, so here's the game plan. First, we're going to figure out what a fluid even is. Then we'll talk about the two languages you absolutely have to speak to measure them. After that, we'll get into their internal stickiness, and we'll finish up with something you use all the time, pressure. Let's just build this up piece by piece, starting with the most fundamental question.
So what really makes something a fluid? You might think, well, it's wet, right? But it's actually way more interesting than that. The real difference is all about how it reacts to being pushed around.
To really get this, we have to look at the official definition. And I'm telling you, the whole thing comes down to one single, really important word.
Okay, see that word? Continuously? That is everything. That one word is the entire difference between something that's solid and something that's a fluid.
Think about it like this. If you push on a solid copper plate, sure, it might bend a little, but then it stops moving. Now imagine putting that same plate on top of some water and giving it the same push. Does it ever stop? No way. It just keeps on going. It deforms continuously. And that right there is the big idea.
But of course, some things like to break the rules. Take toothpaste. You can take the cap off, turn it upside down, and nothing happens. It just sits there. It's not flowing. So what's going on? Well, that's because toothpaste is what we call a non-Newtonian fluid. It's a fancy term, but all it really means is that, unlike water or air, you have to give it a little push first. You have to apply some stress before it decides to actually start behaving like a fluid. Okay, so now we know what a fluid is. The next logical question is, how do we measure it? And this is where things can get a little tricky in the real world, because in engineering, you kind of have to be bilingual.
Seriously, in the engineering world, especially if you're working in the US, you're going to have to speak two completely different languages when it comes to units. It's just how it is.
So on one hand, you've got the super clean, super logical SI system. Newtons, kilograms, meters, makes perfect sense. And on the other hand, you have the British gravitational system, which is what you'll see all over US industry. It uses pounds, feet, and slugs. And yep, you heard me right, slugs.
I mean, the SI system is just beautiful, right? How many millimeters in a meter? 1,000. How many grams in a kilogram? 1,000. Everything is based on tens. Simple.
Now, try to do that with the British system. It's all over the place. There's no simple logic to it. You just have to memorize all these random conversions. And that's exactly why you've got to be fluent in both to really get by.
All right, let's move on to one of the most important properties of any fluid. You can think of it as its internal friction, or maybe its stickiness. And this idea is absolutely critical for everything from the oil in your car's engine to how air flows over an airplane wing.
So this property has a name. It's called viscosity, and we use the Greek letter mu to represent it. Put simply, viscosity is just a measure of how much a fluid fights back against being pushed around. It's the fluid's resistance to flow.
So how do we actually put a number on this stickiness? Well, it all comes down to this one key equation. Viscosity, that little mu right there, is the magic link. It connects the force you're applying, which is the shearing stress, tau, to how fast the fluid actually moves. So the stickier the fluid, the higher the viscosity, and the more force it's going to take to get it going.
And this chart just lays it out perfectly. For the exact same kind of motion, look at the difference. Oil is super viscous, so it creates a lot of stress. Water's there in the middle. And air? Air has a really low viscosity, so it creates hardly any stress at all. Pretty cool, right?
Now, the fluids we've been talking about, air, water, oil, they're called Newtonian fluids. That just means their viscosity, their stickiness, stays the same. But a lot of other things like latex paint or even quicksand are non-Newtonian. Their stickiness actually changes depending on the stress. That's why paint is thick in the can, but spreads easily when you put it on with a brush.
Okay, last big topic, pressure. This is something you deal with every single day, but what you might not realize is that it actually comes in two totally different flavors. First, you've got gauge pressure. This is always measured relative to the air pressure of the world around you. And then you've got absolute pressure, which is measured relative to a perfect vacuum, what you could call a true zero pressure.
Let's make this super simple with an example we all know, your car tires. You ask someone their tire pressure, they'll say something like 32 pounds. What they really mean is 32 pounds per square inch, or PSI. But which kind of pressure is that, gauge or absolute?
That number you see on the gauge, that 32 psi, that is gauge pressure. It's only measuring the pressure inside the tire that's above the atmospheric pressure that's already pushing on the outside of the tire.
And this shows you exactly how to get from one to the other. It's pretty straightforward. You just take your gauge reading, let's say it's 30 psi-G, and you add the standard atmospheric pressure, which is about 14.7 psi. And voila, you get the absolute pressure, 44.7 psia.
So the next time you go to check your tires, just remember, there's a little more to that number than you might think. From the air we breathe to the oil in our cars, understanding these simple ideas really does change how you see the world. It's all about your frame of reference.